solving partial differential equations using Fourier transforms of one kind or another. And I've said it before, to me, on these types of problems, one of the more difficult things, more subtle things to figure out is you have partial differential equations in two variables. Which one do you take the transform with respect to? And which transform do you use? Fourier transform, sine transform, or the cosine transform? Where did I put it? Here is my little rules for which of those to choose. For one thing, any variable we take it with respect to has to show up as a second partial derivative. And secondly, the range of that variable is either infinite or semi-infinite. It goes out to infinity on one end or the other, or both. And here are the other little rules that go along with that. Yeah, the range is, if the range is truly infinite, meaning all the way from minus infinity to infinity, use the Fourier transform. If it's semi-infinite, then you look for the initial condition. Now, we've already said here that we're picking x as the one we take it with respect. So if the initial condition is on the function itself, initial meaning where the variable we're looking at is 0, x in this case, and we use the sine transform. If we're given the derivative of the function at that initial condition, we use the cosine transform. We already did another example, which was almost exactly like this, example 1. Right here, you see only the x comes as a second derivative, and it's an infinite range. So you're going to use the Fourier transform on x, or with respect to x. And we went through that problem. And by the way, when you use the Fourier transform, you usually end up, or you will end up with this little headache of making everything real. You have to deal with complex answers and get rid of the imaginary part correctly. Anyway, let's go to another example. It's the same partial differential equation. So we're looking at taking some kind of transform with respect to x, not t. The range is semi-infinite. This right here tells us we're either using the sine transform or the cosine transform. Here it's a little tricky. We're given this initial condition, and it's just on the function itself. So we'll use the sine transform. Now, neither of these conditions had to do with the derivative of u. We'll use the sine transform. I give a hint here because we're going to encounter an ordinary differential equation that, say, isn't on our formula sheet. When I do that to my students, I give it as a hint in the problem. So let's look at that. K times, what is this for using the sine function? Go back to our formula sheet. Here's the transform, the sine transform of this thing. Go back to the formula sheet. Where is it? Here's our formula sheet. Here's, if it's the sine, minus alpha squared big U plus this alpha times little u. There it is from our formula sheet. And on the right, it's just the ordinary first partial derivative with respect to t. Rearrange terms, and you have this differential equation, ordinary differential equation. That fits this format. This lambda here will be a k alpha squared. And this k here is a different k. This K is not that K. Sorry about that. But if it's just some constant, what's over here in the answer is that same constant divided by the lambda. And here our constant on the right is this thing, different K again. If I divide it by this K alpha squared, end up with u sub 0 over alpha. Anyway, here's the solution that we got from the hint. Now we have to find big A. We also have to transform the initial condition. Let's see here, when T is 0, we're given, what were we given? We like to use 0 conditions when we can. So when T is 0, big U, we also plug in 0 for T, and it needs to be 0. So big U, we plug in 0 for T. What was our solution for T? Plug in 0 for T, this becomes 1, and we just have big A plus this. There it is, and that has to equal the right side of that, which was 0. So now we know what big A is. Plug it back into what we already had, and here is our sine transform of the solution. Not the solution, but the sine transform. The good thing about these sines and cosine transforms is that you don't have to mess with the imaginary stuff. It's automatically a real answer. So we just put it in our formula for the inverse sine transform. Basically this. You can pull out things that don't have to do with alpha. Here's our simplified answer.